What is the purpose of studying the secrets of nature in the four basic arithmetic operations? The essence of numbers lie in arithmetic. Not all numerals are numbers. The Pythagoras theorem is a statement that the area of a square that has the hypotenuse of an equilateral triangle as a side is equal to the sum of the areas of two squares that has the two remaining sides of the triangle of their sides. Pythagoras summarized a variety of principles that exist in the world into one statement: all is number. Pythagoras assigned each numeral a special meaning. It is said that Pythagoras sacrificed 100 oxen to the heavens when he discovered the Pythagoras Theorem. As such, Pythagoras truly admired the principles of numbers discovered all around the world. However, Greek philosopher Aristotle criticized Pythagoras for attributing a necessary meaning to numbers and not accepting them for what they are. What do numbers mean to us? What do we make of them? How could we define numbers properly? According to mathematicians, the essence of numbers lie in arithmetic operations, such as addition, subtraction, multiplication, and division. For example, phone numbers and social security numbers cannot be used in arithmetic operations, and they are no more than a series of numbers. Such numerals are not numbers. Sure, we could add or multiply them, but the results would have no meaning. On the other hand, if the arithmetic operations were possible without numerals, could we call this a number? Imagine two different points on a number line. These points are not numerals. However, in mathematics, it is possible to add and multiply these points. To do so, we need a reference point, such as the numeral 0. On the number line, the reference point plays the role of the numeral 0. This makes the 2 points numbers. Points are not the only things we could do arithmetic operations with despite not being numerals. In mathematics, it is also possible to add two three-dimensional figures. If we add two donut-shaped figures together, we get shape, which symbolizes infinity. There is also a reference point that acts as a 0 when adding three-dimensional figures. It is the sphere. The donut shape does not change even when you add a sphere to it. How could we comprehend the statement, figures are linked to numbers? Let us expand our understanding a little. Think back to when you learned addition in elementary school. Some of us may have memories of a time when the teacher said a numeral of a particular shape has a numeral of a different shape create a third numeral of a certain shape. It did not matter how carefully the teacher explained it. Some of us with such memory may do so because we were used to numerals at the time. That is, we did not understand that the essence of numbers lies not in numerals but in arithmetic operations. Then, how much of arithmetic operations is possible? How are we to define the scope of numbers? The picture on the right is a Feynman diagram, designed by legendary physicist Richard Feynman. It shows the algorithm for particles, where when the electron and positron meet, both are annihilated and becomes light. This can also be expressed as an equation. Let us go back to the fundamental problem of numbers. What are numbers? Earlier on, we define numbers as something that can be used in arithmetic operations. Today, we learn at school that zero and negative numbers obviously exist. Yet, their introduction to mathematics is a relatively recent phenomenon. We do not even need to go into irrational numbers that represent the rules of nature. Anyhow, the concept of numbers has gradually expanded over time, from natural numbers to whole numbers, from whole numbers to rational numbers, from rational numbers to irrational numbers, and from irrational numbers to imaginary numbers. These numbers became the numbers we all learn in school. We also know that points, figures, and particles are all included in numbers. Everything in the universe is made up of particles. These particles are also numbers. The teachings of the great ancient Greek mathematician Pythagoras from 2,600 years ago has finally returned to modern mathematics. In the end, all is number. The four basic arithmetic operations consist of addition, subtraction, multiplication, and division. There is little need to specifically lay out the reason for studying the four arithmetic operations. The four basic arithmetic operations are a method of calculating that is always being used in our daily lives. From calculating how much we have to pay and how much change to get back, to calculating how many items are in a bundle, and calculating how to divide sweets among friends equally. We study the mathematical topic of arithmetic operations, as without them, we would not be able to calculate money or count the number of items we have. Addition includes both the meaning of merging and adding. If there are 2 pencils on the left and 3 on the right, we have a total of 5 pencils. Thus, 2 plus 3 becomes 5. We call this addition of separate objects merging. If we have 2 pencils and our parents give us 3 more, we once again have 5 pencils in total. Although the results are the same, the addition of something new to something that we originally is called adding. Subtraction also contains 2 meanings. One is the meaning of leftover, as in how much was taken away from the original and how much is left. The other is the difference, where we look at the difference in amount between 2 objects. Multiplication and division were created to make addition and subtraction more convenient. For example, we use multiplication because it is tedious to continuously add the same number. The word multiplication indicates comparison in that we can calculate how much bigger or smaller the size of a number or amount is. When objects are scattered here and there, we could count them one by one, but it is much more convenient to use multiplication. By lining up the objects into rows with even number of objects, we can easily figure out how many there are using multiplication. We use division to divide something evenly. For example, consider ways to distribute 10 balloons to 5 people evenly. We could give the people balloons one by one, or we could just give out 2 balloons to each person. Thus, division contains the meaning of division into equal parts and inclusion. Just as multiplication helps do addition more easily, division helps with subtraction. It is much easier and convenient to calculate at once using division than subtracting the same number over and over again. Let us now look at rules of arithmetic operations. Addition and multiplication have a very interesting common rule. First of all, in addition, 1 plus 2 equals 3. Even if we change the order of the numbers around the addition symbol, we still get the same result. 2 plus 1 equals 3. This is the same for multiplication. 2 times 3 equals 6 is also 3 times 2 equals 6 even if we change the order of the numbers around the multiplication symbol. However, the answer changes completely when we change the order of the numbers in subtraction. For example, 3 minus 1 equals 2, but if we change the order of the 3 and 1, we do not get 2. This is the same for division. 6 divided by 3 equals 2, but if we change the order of the 6 and 3 we do not get 2. Commutativity property indicates that the order of the numbers of formula can be switched as in the cases of addition and multiplication. We say it is commutative when the results remain the same. Now let's look at the arithmetic operations that adopts the associative properties. The associative property states that the order in which you calculate the numbers within a formula does not affect the result. Let us first look at addition. Parenthesis 1 plus 3 parenthesis plus 4 equals 8. 1 plus parenthesis 3 plus 4 parenthesis equals 8. In the formulas above, we get 8 both when if you first calculate 1 plus 3, and then add 4, and when we add 3 plus 4, first and then add 1. Thus, the associative property stands in additions. What about multiplication? Parenthesis 2 times 3 parenthesis times 4 equals 24. 2 times parenthesis 3 times 4 parenthesis equals 24. In the formula above, whether we first calculate 2 times 3, and then multiply 4 or calculate 3 times 4, first and then multiply 2, we both get 24. Thus, multiplications have associative property. Do subtractions have the associative property? Parenthesis 9 minus 4 parenthesis minus 3 equals 2. 9 minus parenthesis 4 minus 3 parenthesis equals 8. In the formula above, if we first calculate 9 minus 4, and then subtract 3, we get 2. However, if we first calculate 4 minus 3, and then calculate 1, which is 9 minus 1, we get 8, not 2. Thus, subtractions do not have associative property. Lastly, let's see associative property it holds for division. Parenthesis 24 divided by 4 parenthesis divided by 2 equals 3. 24 divided by parenthesis 4 divided by 2 parenthesis equals 12. If we calculate 24 divided by 4, first and then divide by 2, we get 3, but if we calculate 4 divided by 2, first and then divide 24 by the answer, 2, we get 12, not 2. So, divisions also do not have associative properties. When the result does not change when we change the order of calculations as in the cases of addition or multiplication, we say that the associative property holds. Now let's look at the order in calculating formulas. How should we calculate formula like 2 plus 3 times 2 minus 6 divided by 2 that has addition, multiplication, subtraction, and division all mixed together? In such cases, we need to do the multiplication and division first and then do the addition and subtraction. For the formula above, if we find the multiplication and division and calculate in order, we get 3 times 2 equals 6 and 6 divided by 2 equals 3. The formula becomes 2 plus 6 minus 3, Then we just have to do the addition and subtraction starting from the front. So, we have 2 plus 6 equals 8, and we ultimately get 8 minus 3 equals 5. If we wanted to calculate additions before multiplications or divisions in mixed operations with a combination of addition, multiplication, subtraction, we can put parentheses around areas we want to calculate first. This way, we would calculate the addition first, then multiplication and division, and lastly subtraction. If the subtraction part was put in parentheses, we would first calculate the subtraction, then multiplication, division, and then addition. To summarize the order of operations, we first calculate whatever is in the parentheses, second, do the multiplication and division in the order it is presented, and lastly do the addition and subtraction starting from the front. This is a very important rule in arithmetic operations that we need to pay attention to. Then who decided this order of calculation? The order of operations of the basic arithmetic operations is a kind of promise that all countries around the world abide by. The rule to do multiplication and division before addition and subtraction did not come about because there was some specific reason to do so. Rather, those that studied math had a habit of doing multiplication and division first and putting parentheses around addition and subtractions when needed since a long time ago. They knew from experience that these daily habits are much more convenient to keep than to calculate addition and subtraction first and put parentheses around multiplication and division when needed. This naturally hardened as a rule we use today. What logical arithmetic process is needed for numerals to become numbers? To be good at addition and subtraction, we must be well aware of carrying over and borrowing. Carrying over is a method of calculation where if the sum of numbers from the same place value is greater than or equal to 10, the 10 is carried over to the higher place value. Borrowing is a calculation method used in subtraction. When we cannot subtract the numbers in the same value, we borrow 10 from the higher place value to do the calculation. When doing additions and subtractions, where we use carrying over and borrowing, it is more convenient to calculate starting from the ones place value. It is very easy to do additions and subtractions with just a bit of calculation practice once we understand the principles of carrying over and borrowing. Multiplications and divisions are easy to do through a multiplication table. A multiplication table shows the products of numbers 1 through 9, each multiplied by numbers 1 through 9. It is easier to convert 3 plus 3 plus 3 plus 3 plus 3, adding 3, 5 times, into a multiplication form, 3 times 5. Of course, there are also instances where multiplications or divisions are not necessary. Any number multiplied by 1 is the number itself, and any number multiplied by 0 is always 0. Also, any number divided by 1 keeps the number itself, but a number divided by 0 is not an object of mathematical study. Why did the Asians call the multiplication table a 9-9 table? The term 9-9 was first used in China during the Yuan dynasty in the 13th century. The times table was called 9-9 because the Chinese started memorizing the table from 9 times 9 equals 81. The reason the Chinese started memorizing from the 9s when it would have been clearly easier to start from the lower numbers, is because most of those that memorized it were the nobles. They started memorizing from the top down because they wanted to show they were superior to the others and make multiplication appear difficult to commoners. In the West, the times table started to be used in the ancient Greek era. The ancient Greeks called the multiplication table the table of Pythagoras. Because it was not easy for the Western people to memorize the multiplication just orally, they made a table to help. Divisions are easy to do when we think of them as a backward process from multiplication. For example, when we calculate 10 divided by 2, we can think of the 2's in multiplication. 2 times 5 equals 10. Thus, it is easy to know that if we divide 10 by 2 we get 5. Of course, we could have calculated this by subtracting 2 from 10 repeatedly and seeing how many times we need to do so. However, this method becomes inconvenient as the number becomes bigger. Arithmetic operations and calculations are different from one another. In arithmetic operations, there are properties of numbers, like commutative property, associative property, and distributive property. However, with calculations, we just have to find the results for a formula. Most problems children learn in school that requires calculations follow a standard algorithm. Children think they are practicing arithmetic operations while all they are really doing is exercises on how to calculate. This is why most students find math boring and eventually give up on math. When we are teaching children a curriculum on arithmetic, it should be arithmetic-based, not calculation-based. This way, the students will still be interested in mathematics as they go up to middle and high school. A method of learning addition through a determined algorithm would be to think the addition of 1's value and the carry over whatever is necessary to the 10's value. However, let's break away from this dull method and think of the students as being in a primitive state, where they know nothing at all. Let's say we have 36 apples and want to add 27 more apples to it. There are many ways to do additions. One is to line up the 36 apples in one line and add 27 apples to the same line. This method of adding up is one of the definitions for addition. As we line up the new apples one by one, we would go 36, 37, 38, and so on. Another way is to put the apples into two groups. Put the 36 apples in one basket and the 27 in another. Then, combine the two baskets together. This is adding by merging. There is a definite distinction between the two methods above. When children understand addition as just a method where you add the 1's place first and carry over 10 to the 10's place when needed, they quickly lose interest in mathematics. If they simply just memorize the standard algorithm for addition, which is the easiest way to learn it, children will no longer feel the need to come up with creative ideas on how to do addition. That is, they will no longer try to understand and be interested in doing addition through the adding on method or the merging of two groups method. Doing arithmetic by counting in groups uses the base 10 system of Arabic numerals. Group the 36 apples and 27 apples into groups of 10 and separate the remaining apples. By doing so, we see that we have 3 groups of 10 and another 2 groups of 10 with 6 and 7 individual apples. Add the individual apples, 6 and 7, and we get 13. If the sum of the individual apples is more than 10 as in this case, we can make a group of 10 and add it to the groups of 10. Originally, there were 5 groups of 10 in total, and with the addition of another group, we now have 6 groups of 10 and 3 individual apples. Using this method, students can have first experience and understand the need to carry over while doing addition. Calculations after such mathematical experience allow children to fully understand the meaning of calculations, while also understanding the properties of numbers in the base 10 system. Subtraction works the same way as addition. If we practice and get a sense of subtraction using branches or matches without jumping right into the column method of calculation according to the given algorithm, our creativity will flourish. For example, try to solve for 60 minus 27 using matches. One way of doing this would be to take out 27 matches from 60 matches one by one and then count the remaining. This method is tedious, but the calculations are easy. We could also calculate with groups of 10. 60 matches are 6 groups of 10 matches and there is no remaining. 27 matches have 2 groups of 10 matches with 7 remaining. When we subtract 2 groups of matches from 6 groups of 10 matches, the 4 groups remain. We now need to calculate the single matches, but we cannot subtract 7 from 0. So, we can take the group of matches and make 10 one matches, then go on to take out 7 matches. In the end, we have 3 groups of 10 matches and 3 remaining matches. In this process, students can easily understand what borrowing is because individual units can be subtracted only when one group of 10 is converted to 10 individual units. Students who simply do the column method of subtraction according to what they have memorized do not know why they should borrow values from the higher place value. Their mechanical approach to calculations causes difficulty in understanding the logic behind subtraction. For addition and subtraction, it is more convenient to start calculations from individual units, then go on to groups of 10 units. To put it another way, it is better to calculate from the ones place value. However, in the case of division, we first calculate the groups of 10 units, meaning that we start calculations from the tens place value instead of the ones place value. Why do we start calculations from the lower place value when doing additions and subtractions while we calculate from the higher place value when performing divisions? Of course, we can also do additions and subtractions can start from the higher place value. In the case of calculations that do not require borrowing or carrying over values, it is easier and more convenient to calculate from the higher place value. In fact, many children have a habit of doing calculations from the higher place value. However, this creates difficulties for additions and subtractions problems requiring carrying over or borrowing values. Children stop thinking once they learn how to calculate according to the algorithm. From this moment on, calculations become puzzles to them. The children who have a strong sense of number can easily calculate. For example, show children an appropriate size box to show the number of students in a class. If a child has a good sense of number, he or she would make a close estimate of the actual number of students of the class, like 20, 25, or 35 students just by looking at the square box. However, if another child made an estimate like 1,000 or 2,000, that is too large to be the number of students in a class, we may say that this child lacks a sense of numbers. This natural understanding of numbers is called the sense of numbers. Because there are too many ways of doing calculations, it is not adequate to just demonstrate a process of calculations and its results to children in order for them to develop a sense of numbers. We need to let children to carefully observe the object and try to find its unique characteristics. We must also give them enough time so that they can come up with effective and convenient ways to calculate on their own. When we look at children doing multiplication, many of them use the times table, which they are so familiar with since they have memorized it from an early age, or use a pencil and paper to write down the multiplication process. What would they do if they are asked to calculate in mental arithmetic? The questions like how can we do mental arithmetic, or is there an easy way to do mental arithmetic using a special number, would come across their minds. If the number that makes calculations easier is fractions, the examples would be numbers like 1/2 and 1/4. Children easily understand the concept of half in daily lives. Moreover, if we understood the property of the number 25 and 96, we could think of 96 in the following way. Because 96 is 96 equals 100 minus 4 and 100 is 25 times 4, we can easily think of 96 as 25 times 4 minus 4. In order for children to develop the sense of numbers, they need to shift their focus to the arithmetic operations and learn how to utilize the rule of the arithmetic operations using the property of numbers instead of doing simple and repeated calculations. They also need to learn the unique property that numbers have. Numbers are what we can perform arithmetic operations with, but if all we can do is simple calculations, they remain being no more than numerals. This is the difference between numbers and numerals. No matter how fast we can calculate, a lack of the capacity to think would render problem solving difficult. It would mean that if the problem is changed ever so slightly or if the problem is difficult, we just give up. The familiar column method of calculation should be taught as the final step in studying arithmetic operations. The use of graph paper when studying multiplication allows us to recognize the principle of multiplication accurately. We should first practice the times tables in the form of one-digit number times one-digit number, go on to practice one-digit number times multiples of 10, like 3 times 10, and multiples of 10 times multiples of 10. If we then move on to calculate two-digit number times one-digit number and two-digit number times two-digit number, all forms of multiplication would feel easy. However, when we look into mathematics education in various countries, a study of multiplication is scattered throughout the curriculum. This is why we often see students who have understood how to solve the multiplication of two-digit number times two-digit number well struggle to solve three-digit number times three-digit number problems. Why does this happen? This happens because students do not properly understand the principle of multiplication. Thus, it is necessary to use graph paper when studying multiplication. When solving 12 times 3, students who simply studied multiplication according to the standard algorithm would just focus on calculating mechanically without understanding the property of numbers or the principle of multiplication. By using graph paper, we can divide the number 12 into the number 10 and 2. We can also know that when we multiply 3 to each of 10 and 2, it becomes 30 and 6 and 36 by adding two numbers together. Some people might ask why 12 is divided into 10 and 2 when there are other ways to divide it like 9 and 3. However, as we use graph paper, we can easily realize that it is convenient to calculate in groups of 10. Mathematics curriculum in elementary school does not widely use a term distributive rule. However, by seeing how calculations are done using graph paper, students can realize that they can get this answer through this process by themselves. Even if students cannot explain what the distributive law is exactly, they can understand what it is indirectly by using graph paper. Numbers and arithmetic operations are not so simple. Knowing how to distinguish between numbers and numerals and recognizing the mathematical logic that numerals need to be usable for arithmetic operations to be numbers is more important than anything else. Lastly, we can also develop the ability to create multiplication equations that make multiplication easier by using the graph paper. For example, suppose we want to calculate 12 times 25. We would be able to find that we would be able to calculate more easily if we turned it into an equation with 0 in the ones place, as in 12 times 25 equals 6 times 2 times 25 equals 6 times 50 equals 300. How could we utilize our understanding of the arithmetic operations? We cannot properly get the information necessary in our daily lives without knowing the four basic arithmetic operations. Let us take a look at a problem involving the size of the population. Suppose the population has been doubled over the past 50 years. That is, if there were 100 people 50 years ago, we now have 200 people. Today, the world population increases by 76 million every year. Thus, we need to add 76 million to the original world population every year. However, some news reports that the population of the world is likely to decrease in the future. Since the year 1960 in Poland, children under 5 years of age is said to have decreased by half. On a global scale, the number of children under the age of 4 decreased by 6 million since 1990. We need the workings of multiplication, addition, subtraction, and division to fully understand this phenomenon. We can play a fun mathematics game using the four basic arithmetic operations. By filling up a 3x3 grid using digits from 1 to 9 exactly once, we can make a combination of digits so that the horizontal, vertical, and diagonal sum of 3 digits are always the same as 15. This is called a magic square. People of the past are said to have always carried the magic square with them because they believed that it had magical powers. The reason why each row of a magic square adds up to 15 is as follows. The sum of all the digits from 1 through 9 is 45, and the sum of each row with 3 of the 9 numbers have to be the same. Thus, the sum of any combination of 3 digits in a row should be equal to 15, the number of dividing 45 by 3. The four basic arithmetic operations need to be used according to situations. Take the example from a familiar story of King Solomon's judgment. One day, two women came to Solomon with a baby. Both women claimed to be the mother of the baby. . Solomon brought a sword and said, "This is my judgment. Cut the baby in two with this sword, and each of you may take a half. One of the women begged Solomon not to kill the baby and said that she'd give the baby up to the other woman. Solomon declared that the woman who gave up the baby was the true mother. This story teaches a lesson that it is problematic to see the world using divisions by two. Now let us think about methods finding out rules in the relationship of the arithmetic operations. Even in the case of solving somewhat complicated problems of arithmetic operations, it may be necessary to find rules and make deductions accordingly. It is best to start with simple rules and gradually move on to more complicated ones. To do so, we would first examine several simple forms and observe the changes. Every change affects rules. Thus, if we would take a careful look at changes, we would be able to find rules. As we are looking for rules and changes, it may be best to bring out as much change as possible. To apply rules found from observing several simple cases to every case, we must also figure out the exact reason why the rules appear. One example is the multiplication table. That is, the multiplication table shows every product of numbers 1 to 9 multiplied by numbers from 1 to 9. We solve for 2 plus 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 2 by using multiplication like 2 times 8. As such, the knowledge of the multiplication table and memorizing it allows us to multiply much faster. Once we also learn the rules in the multiplication table, we can remember it much more easily. The 3 and 5 times tables have the following rule. The values in the 3 times table increase by 3, as in 3, 6, 9, 12, and so on, and the values in the 5 times table increase by 5, as in 10, 15, 20, and so on. What about the 1 and 0 times tables? When any number is multiplied by 1, it always becomes the number itself. As such, any number multiplied by 1 stays the same. Thus, the values in the 1 times table increase by 1. In contrast, 0 is a special number that makes any number, which is multiplied by 0, becomes 0. If a computer received an electrical signal which is slightly higher than 1 volt, the computer could process it as 1 volt and transmit the digit 1, or as 2 volts and transmit the digit 2 because the signal was greater than 1 volt. As such, to reduce errors in data transmission, the computers use the binary system, representing the digit 1 when there is an electrical signal and the digit 0 when there is no electrical signal. This time, let us look at the secret of barcodes that contain the concept of one-to-one correspondence. On the packaging of products used in our daily lives, we can easily see barcodes consisting of black lines and white gaps. When we go grocery shopping, we choose and put items on a checkout counter. A clerk would read barcodes using a barcode scanner, which beeps and the price of the items are displayed on the monitor. Thanks to barcodes, it became no longer necessary to enter every single data of products one by one. Why does a barcode use the shape of sticks instead of numbers? The barcode uses the black and white lines so that computers, which represent information using 0 and 1, can read the information easily. By the way, why are there seemingly meaningless numerals below the barcode? Sometimes, the barcode scanner does not work, and a clerk may have to type the numerals in barcodes one by one using a keyboard when the barcodes were not readable. That is, the numbers are there in case barcodes cannot be read because they are erased or damaged. Barcodes are usually made up of 13 digits and each digit has a different meaning. The very first 3 digits show the country the product was manufactured in, the following 4 digits represent the manufacturer, the 5 digits that come after indicates the unique code for the product. The final numeral is a check digit to verify whether the preceding digits are right or wrong. This check digit is determined by the first 12 digits. The check digit can be calculated by adding the sum of digits in the odd-numbered places and the sum of digits in the even-numbered places multiplied by 3. The final sum becomes a multiple of 10. Some people may think that barcodes are too complicated to understand. However, when we look into them through mathematics, we can know that the principles of barcodes are very simple.